Okay, good morning everyone. Hope you can hear me over the superconducting guys next door. So did they? I'm going to speak up a bit. So thank you for the organisers for inviting us to this fabulous place. I'm going to talk, really a corollary in fact to Ian's talk. I'm going to talk about site control of quantum dots by MOVPE and by a particular growth technique which is droplet epitaxy in MOVPE. And I'm going to talk about really the development of the science into technology. And this should work. I need to point that way probably, do I? There we go. So first of all, a few acknowledgements to the people who have contributed to all the results in this work. Most of the work is done at the University of Sheffield, and in Sheffield, semiconductor activities are split between Department of Electrical Engineering and Physics, and including the National Epitaxy facility, which I will describe later. So we have a number of people associated with the Epitaxy facility, and then a large group in the Department of Physics, led by Maurice Skolnick. I also want to thank our collaborators in Toshiba, including Joanna, Mark Stevenson, and Andrew Shields. Also for work on STM measurements, Paul and his colleagues at Technical University of Eindhoven. And of course, I'd like to thank our funders, which is mainly the Engineering Physical Sciences Research Council in the UK, but also Innovate UK, which funds industry-led projects at a higher TRL level. So, before getting stuck into quantum dots, I'd like to describe a little bit about what actually is happening in quantum technology in the UK. As you know, quantum technology is a very hot topic worldwide, with a lot of investment and a lot of growth in this area. In the UK, the government established a £1 billion programme in quantum technologies in 2014, and there was a second phase to that which started in 2019. And like many countries, a strong technological focus in quantum computing, communications, sensing, and metrology. And in particular in these four areas, one of the big things that was established was a group of hubs associated with each of these technology areas. So quantum computing hub in Oxford, communications hub in York, sensing in Glasgow, and metrology in Birmingham. So these are large hubs. They involve a lot of research, academic research as well as industry research, and then also there's a large number of academic organisations who are part of the hub. So overall, these are the coordinating functions within the UK for certainly the development of quantum technology. As part of the programme, there's also been a national quantum computing centre that was set up in Oxford, and again this is coordinating assets to deliver on quantum computing. So it's a large programme. They are now looking at the next phase of this. Some impressive numbers with it. Actually, in particular, this number here is over 49 startups in the UK, and this is only in an 8-year period. 49 startups in this area. 470 PhD students being supported now directly under this quantum technology programme. So this is the background, and actually a lot of the work that we do in Sheffield is funded through this programme. We, of course, have long-standing expertise in quantum technology in Sheffield, and we pulled all this together into a Sheffield Quantum Centre in 2019. Oop, and I did not want to do that. I don't think I did press the button, but let me see. Press it again. There we go. So we pulled all our activities together into a quantum centre founded in 2019, and this is across departments of physics, EEE, and computer science. We have a long history, about 40 years in this area, and particularly in the area of quantum photonics. So we're bringing all these strengths together. We have around 70 academics and researchers involved in this area, with currently about 40 million worth of research funding for this. This has led to a number of very good research results, also 3 spin-out companies in the last 4 years, which are now getting significant investment. And it's part of an overall strategy of semiconductors, quantum, and manufacturing, which is a significant strategic activity within the university. So you can find out more at this website address. The other thing I wanted to talk about, get to do that. Yes, is the National Epitaxy Facility. So Sheffield hosts the National Epitaxy Facility. It has done this for about 40 years again. This is a consortium of 3 universities, Sheffield, Cambridge and UCL, and we're a national facility for providing epitaxial services to researchers around the UK. So we basically provide epitaxial wafers for anybody interested in semiconductor research in the UK. We supply to about 25 UK universities as well as some international collaborators. And basically people who don't have epitaxy capability, they can come to us and we will grow their wafers for them. We currently support about 140 million of research projects and also work closely with industry. And in the last 10 years or so, a lot of our work now is actually strongly focused on quantum science and technology. So we have significant resources in the facility, 5 MOVPE systems, 6 MBE systems across a broad range of 3-5 materials and group 4 materials. So we have a capability of doing all kinds of different materials and all kinds of different devices, some of which are listed here. And again, all the work that I'm going to describe in the quantum dots is actually delivered through this National Epitaxy Facility. So let's talk about quantum dots. Well, Ian has already given a good background, but let me give my spin on it, so to speak. So why are we interested in quantum dots? Well, it's 3 important aspects of quantum dots. First of all, we're interested in semiconductor photonics, so we're interested in photons. And semiconductor quantum dots really form an ideal system for making efficient single photons or even entangled photon sources, and also have tunable emission properties, so we can actually make interesting devices and we can control the emission wavelength of those devices. So the ability to create single photons comes from the exciton states within the quantum dot. So you have a variety of different types of exciton states, and if you take just the basic exciton, then you can get a single photon source from the decay of this exciton. But you also have a biexciton state here, so actually with what's called a biexciton cascade, whereby the biexciton decays into 2 excitons, you can actually get 2 entangled photons with orthogonal polarizations. So as long as you have a quantum dot that's very symmetric, these states are degenerate, and so they are fully entangled. And one thing that's important for quantum dots is if you don't have a very good symmetry in the dots, then actually these 2 exciton states can be split. And now the photons are not identical. And a lot of our work has actually been on controlling the shape, size, and the symmetry of the dots in order to get this type of a degenerate system. The other thing is that there are well understood spin states in quantum dots, and you can do a lot of work with spin, and you can do a lot of work with the interaction between spin and the photons, including a number of things like spin to path conversion, which means that you can start thinking about making circuits, which I'll describe later. Probably the most important thing for us in terms of the quantum program that we have, the quantum technology program, is that we are building on the semiconductor industry. So the semiconductor industry is incredibly successful in mass manufacturing for the last 50 years or so. And we believe that if you're going to actually develop quantum technology, you do need to have the ability to scale up, as in the title of my talk here. So there's a significant interest now in integrating many types of devices, including quantum dot single photon emitters, into full semiconductor platforms. For example, here, this is an example of some ideas for semiconductor integrated photonics using quantum dots and a whole range of linear and nonlinear optical techniques. So there's a good review of this in this recent paper. This is an example of some of the work that we've been doing and moving in this direction. So for example, we have here a membrane containing quantum dots, 3-5 quantum dots, which we have lifted off of a 3-5 semiconductor, and now we've put it onto an SOI substrate, and we have SOI waveguides, and we have ring resonators, and we can do add-drop type functionality with this platform. And these are examples that we have of, again, making complex devices like photonic crystals and waveguides for entanglement of photons. So there's been a lot of work done at Sheffield as the scientific building blocks for making the kind of quantum circuits that I've just indicated there. And there's a couple of examples of things that have come out of that work. All this work is basically being done on gallium arsenide based quantum dots. So in particular, you can get, if you include your quantum dot inside a photonic crystal structure or cavity, you can get a high parcel enhancement, and this then means you can shorten the lifetime down to, in this case, about 23 picoseconds. So that gives us the opportunity to do essentially gigahertz coherent quantum photonics, including the possibility of making cluster states. Also, these quantum dots are tunable, and there's a variety of methods, including applying electric field to the dot, but also there's some interesting options in using electrostatics and using proximity effects of different waveguides. So here's an example of two waveguides, and by applying an electrostatic force, we can move them relative to each other, and that gives us a significant tuning of the optical emission of the dots. That allows us to do things like tune the dots in and out of high Q cavities. And this is then very useful for manipulating the single photons that we have. The physics group have demonstrated basically single photon gating. So with this tuning process here, we can actually tune the dots to be in resonance with photons. And in this work here, you can actually show that one single photon can influence the transmission or the reflectivity of another photon mediated through the quantum dot itself. So this is actually the basis of a kind of quantum gate using single photons. And in more recent work, there's been some development of basically chiral properties of single photon emission in waveguides. So this is an example of where if you control the spin and you control the polarization of the photons, you can actually control which direction they move in. So this again is the basis for routing and selective routing of single photons in circuits. So this is the background science, and you can spend your time taking down those references. Okay, so the T in this conference stands for technology. So the question is, how do we translate this quantum science into quantum technology? So two things. In the first, Ian's already introduced this topic. So we need to move from, normally when you grow quantum dots, they grow in random places on the wafer. And we need to move from these random distribution to much more controlled positioning of quantum dots. This is the example of how to create essentially a Hongu-Mandel type arrangement on a chip, so you can interfere two photons, one coming in here, one coming in here, and they get entangled here. In this example, we've used a quantum dot here, but we use a laser here. If you want to do it with two quantum dots, then you need two identical quantum dots, and actually it's very difficult to find those two identical quantum dots here, as well as having other dots in between, which can cause you some problems. So if you imagine making a microprocessor with transistors, and if all your transistors were randomly distributed, you'd have significant problems. And that's really, you can think of this as the kind of optical equivalent, as a quantum equivalent to the transistor. So we really need to move to much more ordered arrays so we can make more complex circuits. We are able to do this, but only with one or two quantum dots. We want to be able to do it tens, hundreds, thousands of dots. The usual way is seeding, as has been explained. So you basically create a nanoscale structure here, and you want the quantum dots to actually form in these nanoscale structures and not in between, and that gives you this kind of regular ordering. So the second aspect of quantum science is, as I said, much of the work that we have done is in gallium arsenide, so that's at 900 nanometers, and a lot of the science has been established at that wavelength. But in fact, for technology, we want to move to longer wavelengths. In particular, we want to use the C band, which is the basis for fiber communications. And the second thing that we want is, so to move to the C band, we move from gallium arsenide to indium phosphide. But the second thing that we want is, although MBE is a fantastic technique, and we loved MBE, probably over the last 30 years, actually MOVPE has been established now as the industrial standard for mass production of semiconductor materials. So we actually want to develop these high quality quantum dots using MOVPE, and that's what we've been doing. That's what the rest of this talk is about. So the quantum dots that we grow are grown in this MOVPE system. This is an X-tron closed coupled showerhead reactor. This is actually a 3x2 system, and it is, we say it's compatible with industry. It's actually very similar to the industrial designs that are much larger numbers of wafers, but anything that we do here can actually be translated mostly into industry. So this is the system that we're developing our quantum dots on to address that second technological issue. So Ian has described already the growth of quantum dots by Stranski-Krastanov method, and that is a method whereby the dots are formed through strain relief. In this structure, you grow indium and you grow arsenic together at the same time, indium arsenide, and when you get to a certain thickness, you get quantum dots formed. By MOVPE, we're investigating a different process. This is the technique of droplet epitaxy. And in that case, it's simpler. So we have a substrate, we apply indium metal, and again, through surface tension and reduction of energy, at some point the indium forms droplets on the surface, and then we expose those droplets to arsenic, and the droplets are converted into indium arsenide quantum dots. So it's an alternative to Stranski-Krastanov. It is not strain-driven, so actually this is not a strain-driven process as it is in the indium arsenide case, and that gives you various advantages. One of the advantages is that we have no wetting layer in the Stranski-Krastanov method. When you have your quantum dots, you have a wetting layer associated with the original thin layer of indium arsenide that you grow, and that can be problematic in a variety of devices, particularly introducing competitive recombination routes and noise into the structure. So we have established over a number of years the growth of indium arsenide quantum dots at 1550 nanometers using droplet epitaxy in MOVPE, and here's an example of an optical spectra in the C-band, and you can see these sharp lines here are associated with individual quantum dots. The line widths that we have typically in this MOVPE reactor, in other words, this industrially compatible MOVPE reactor, are typically around 60 micro EV, but actually we do have a part of this distribution here that is below the resolution limit of our spectrometer, which is around 20 micro EV. So these dots actually are good quality and have good coherence properties. One thing that we found in the MOVPE growth is actually these dots, they form, but they actually form within an etched pit around the dot, and that's actually interesting, but also potentially important in terms of the site control, which I will come on to. So a number of interesting properties of droplet epitaxy that make it useful for devices. We have, because of the fact it doesn't rely on strain, we have reduced in-plane, so you have high symmetry in the dots. We have very good compositional homogeneity. These are actually almost pure indium arsenide quantum dots, which can be challenging in the Stranski-Krastanov method. And we have no reduced shear and biaxial strain associated with the lack of strain-driven process and the wetting layer engineering I mentioned. That means that we have flexibility in what substrates we want to use, the strain-free aspect. The fine structure splitting and the symmetry of the dots appear to be better than at 1550 than the Stranski-Krastanov method. And this has led to long coherence times, and there is reduced noise. We believe there's reduced noise from the wetting layer. But also when we move to indium phosphide, we can actually make even better nanophotonic structures using indium phosphide. So there are a number of advantages that translate into moving to 1550 and also to the droplet epitaxy. So using random quantum dots, we've actually achieved a lot of very good results at 1550 with this droplet epitaxy process, and that's particularly making entangled LEDs, so LEDs that emit entangled photons. And I'm not going to talk much about that because Joanna is going to talk about that tomorrow in her talk. But a number of very good results here, including all the way up to demonstration of teleportation with these devices. But we want to do site control. So how do we do the site control? So we take this novel approach, which is that we want to use the droplet epitaxy approach for site control. So instead of trying to site control the quantum dots directly, what we have looked at is positioning, first of all, the indium droplets, and then the conversion of those indium droplets into dots through the droplet method, but in etched pits. So there's some advantages to this. Strain doesn't control the position of the droplets, so we can remove a constraint from the fabrication. So the fabrication, because the strain affects the quantum dots in often very subtle ways, we would need to control the fabrication of the nanoholes that we use to seed the dots. But if we remove that constraint, then actually things are easier. So that's a significant advantage. Also, the droplet density and the size and the shape are kind of independently controlled through the droplet epitaxy process, so we can actually match some of these properties, especially the density, to the pattern of the site control that we want. No wetting layer means that we don't actually have to worry about the changes to the wetting layer that may occur inside a nanohole inside a seeding nanohole. And you can see here that we've observed, I showed the previous slide, we've observed etching in the dots forming in the pits. So these are some very nice images from Paul's group here that show that under different growth conditions, we have our quantum dots, and you can get some local drilling underneath, but you can also get these dots appear in etched pits. And this is actually interesting because it opens up the possibility for us to shape the dots. And going back to the idea of symmetry of dots and having very small fine structure splitting for entangled photons, the more we can shape dots, the better. And we think that the ability to match this etching and drilling to the nanohole itself is an opportunity for us to look at controlling the shape of the dots. So just to indicate here that we've got some control over this, you can see that at different growth temperatures, actually the dot again appears inside a nanohole, usually a few nanometers deep, but note the scale here. So these actual pits are of the order of about 300 nanometers. 5 minutes? Okay. These pits are of the order of about 300 nanometers, and so they're actually, the pit is about of the same kind of scale at that size that we use for the seeding of the quantum dots in nanoholes. So the interaction of this natural etching process with our fabricated nanoholes is something that is of interest, and that will could allow us to control the shape of the quantum dots. So the process of droplet epitaxy site control, we fabricate these nanoholes, fabricate them by usually E-beam lithography. We do ICP etching to make the nanoholes. They're about 30 to 40 nanometers deep and of the order of 100 to 300 nanometers wide. Then we do a wet chemical clean to make sure the surface is really good before we put it into the MOVPE system. And also before that, we actually confirm that cleanliness using surface SIMS analysis that we have in one of our MBE machines, as well as AFM. Then we grow a buffer layer inside these nanoholes. That is to make sure that any dots that we grow are away from the etched surface, because the etched surfaces can cause noise. Then we deposit the indium, and we hope and expect that the indium will fall into these dots, into these holes, and then we have site control of the indium droplets. Then we crystallize these droplets, and then finally we will cap it with indium phosphide to make the quantum dots that we've formed into optically active quantum dots. So what kind of results do we get when we try this? So the first thing is in terms of fabricating the structure. As I mentioned earlier, we actually do have, through the droplet epitaxy process, independent control of a number of parameters of the dots. In particular, for instance, using the indium time, we can control the density of the dots from around 10 to the 7 up to 10 to the 9 or so. And this is important because we make patterns for the nanoholes, and if we can match the density of the pattern to the density of the dots, or so the other way around, the density of the dots to the density of the pattern, and we increase the chances of actually the site control of the droplets into the pattern that we achieve. Now the precise details of the pattern depends on what we want to do, and in fact for a pattern like this where they're 4 microns apart, the reason we want to do that is because we want to do optical excitation on a single dot, and our excitation spot is about that size. But if we were going to full circuits, we would obviously make much more dense structures, and then we match the density of the dots to that. There has been a significant challenge in the growth of the buffer by MOVPE, and these are quite shallow and narrow nanoholes. And what happens in MOVPE compared to MB is that you get a lot of growth from the sidewall. So actually the control of this buffer layer has been very challenging. We often, when we first grew, we got initially planarization. In other words, we removed the pattern. So we've had to develop this to make sure that we get good buffer layer formation within those holes. And finally, when we supply the indium, then indeed we do see that the indium forms in the holes, and that this happens at different pitches. In the case of 1.5 micron pitch, we actually have good statistics. We've got about 70% occupancy. In other words, 70% of the holes have a droplet in them, and we get no interstitials. In other words, we get no droplets in between these holes. Okay, so that's not bad. That's fairly good, actually. When we go to the 4 micron pitch that we show here, where you've actually got a lot longer distance for the indium to diffuse into the holes, we actually get about 100%. We get 100% occupancy in this case, but we do get quite a lot of interstitials here. So somewhere between these two is an optimum, and as long as that optimum allows us to do optical measurements, we're happy with that. A couple of interesting things that I'm not going to dwell on, but you can see actually that the droplets don't form at the center of the hole, so they actually form at the edges of the hole. And we believe this is related to essentially the contact angle between the droplet around the hole. But also there is something of a crystallographic direction to that as well. And we're not entirely sure why that is, but we have some ideas that it may be related to the etching and elongation. So I probably have about two minutes left, really. So good success. Droplets are nicely site controlled in the holes. If we supply arsenic and convert them to quantum dots, what happens? Do they disappear or do they not disappear? And the answer is they don't disappear, but some interesting things happen. So what happens when we apply the arsenic and convert to quantum dots is that actually we do get quantum dots and we do get the site control. So actually we have about 80% occupancy of dots. But interestingly, we form 2 dots in the holes. Also, the dots form in the middle of the hole rather than on the edge. So actually the presence of arsenic causes significant redistribution of the indium. We get mass transport of this process, and we've seen this in the random dots as well. And so actually we go from droplets around the edge to dots in the middle. We also get quite a lot of clumping, so this actually tells us that in between the holes, even though we can't see it very well in AFM, we do seem to have quite a lot of indium. And when you apply the arsenic, the indium moves around, so that allows us to get site control of dots, but it also causes quite a lot of clumping of indium. So we are still in the process of optimizing this, and I think we just need to reduce the amount of indium. That may also control how many dots that we have in the site control. So this is good news because it means that the process works. We can site control the indium drops, we can take the advantages that we've discussed about lack of strain, etc., and we can play around with the interaction between the droplet and the hole and etching, but we can maintain the site control when we convert into dots. This is only AFM images, so what we need to do is show that we get good quality dots. So we have to cap these, and again we've capped them in indium phosphide. And we do see evidence of dots. This is a kind of a macros PL measurement of our quantum dots around 1400 to 1600. At the moment we don't see single quantum dots. They're quite dim, and that means that we need to optimize the capping process. But at least we do see an optical signature of these dots. Once we've optimized the capping process, then we'll start looking at single dots. We'll look at the lifetimes, look at coherence, etc. of these dots. So, in summary, we have established droplet epitaxy of indium arsenide and indium phosphide quantum dots via MOVPE. We have indium droplets to indium arsenide quantum dots by arsenic crystallization. We've controlled the densities for about 10 to the 7 to 10 to 9, as well as other properties. And the random dots show excellent properties, and we've demonstrated a number of things with these random dots, both with single and entangled photons in the C-band. But we've been investigating site control. So site control of indium droplets has been demonstrated with good occupancy statistics. Site control is maintained when the droplets are crystallized into indium arsenide quantum dots, maintaining the good occupancy statistics. And we have the first evidence of optical emission of site control by this method. So our next steps are to improve the buffer layer growth and establish high efficiency quantum dots and get that optical efficiency up. But we also are looking at better control of the crystallization to produce single quantum dots in the hole, and also control the uniformity of those dots and explore the question of the interaction of the droplet etching with the hole itself, which may help us to control the symmetry of the dot. And ultimately then we're looking for low line width dots, high coherence, which will be partly a test of our fabrication quality. And once we have that, we can make the kind of structures I showed earlier with nanophotonic devices around identical dots that are site controlled, which is the basis for quantum photonic technologies in the C-band. And with that, I say thank you very much. Any questions?
May I kick off with
You may apply.
The question is maybe more a remark, or maybe both are more remarks. I think you're completely right when you say that strain is not involved in forming the indium droplets, but I think when you go into the crystallization phase, then the strain, of course, again plays an important role.
Yes, yes.
And do you see that as a problem for your dots, or do you think that's okay?
I think it's okay. I think what we've seen, what I showed there at the end, is that we've got significant amounts of mass transport, actually. So the thing about the strain is that in the SK process, the strain is very strongly controls the dot formation. So it controls the density, it controls the shape and the size, etc. I think by this technique, although you have strain comes back in when you do the crystallization, I think it's less direct because you've got things like the mass transport, for instance. And in particular, what we worry about in site control is that when you fabricate the structure, so you fabricate a nanohole, because the SK is so sensitive to the strain, that actually you've got significant constraint on your fabrication, and particularly on the uniformity of that. So you only need small changes in the structure of your nanohole to then cause you a big problem with the kind of dots that you have in the different holes. So I think it becomes more of a secondary problem than a primary problem in that case.
No, I also see that the purity of the dots is strongly enhanced by going to Droplet.
Yes.
SK dots strongly show inhomogeneity in the material itself, gradient in the indium concentration.
Yeah.
And all of that is going
Yeah,
to
exactly. And you know what I said at the end there, what we want is, I put identical in inverted commas, because actually we do want identical dots, but it's very difficult to get perfectly identical dots, and that means, for instance, dots that are made at exactly the same wavelength. So we do have some control with tuning, but we need them to be fairly close in wavelength. And so actually I think these techniques, like having pure indium arsenide droplets, help us, because if we've got pure indium arsenide droplets, again we remove the alloying aspect of the variation. Now we have much more, now we can just focus on the morphological problems.
And then a small remark I have, are you familiar, I suppose you are, with the work of Emanuel Stelly?
Yes. Yes. Yes.
Who actually grow molecular quantum dots in X-rays.
Yes, yes, yeah. And you know, as you can see here, that's, at the moment we're kind of trying to get rid of it, but in fact, you know, there's some interesting possibilities here in terms of these things. Yeah. And you know, these are quite nice quantum knots here, actually. You know, so.
Sorry, just a couple of, well, maybe one question from my side. I'm very thrilled about your position droplets, extremely thrilled. And I'm looking forward to seeing some optical properties of them, like the lamps.
Yeah.
I think that would be a photonic breakthrough.
Yeah.
To us. I have a question. Have you tried actually positioning them on smaller bits? You said actually that the bits you were using were 300 nanometers.
Yes, we have, yeah, yes.
That would help. And also actually another question, another related question is, how are they etched? Are they dry etched or is it wet etching?
It's dry etch, so it's ICP etch, and then we do a wet chemical clean. No, I think it maintains it fairly well actually, but it's just it's to clean up the surface, particularly for the MOV to put it in the reactor. So at the moment it's dry etch. We are exploring other things like the LAO that Ian mentioned, and possibly even nano imprint type technologies that we use with either etch process. So at the moment it's dry etch, so actually quite steep walls with a little bit of a pit at the end. If we do wet etching, we get much more rounded holes. So I think we've got a number of options of exploring, again, the interaction of the droplet etching with that. So I should say that this is really, this is just kind of a snapshot of a broader study that we've done, which is the size of the holes, the pitch of the holes, the depth of the holes, etc. And these are the kind of the best results from that. Yeah. So I mean, part of what we really want to do is bring the hole size down to have it more matched to the droplet. But we've partly worked on larger holes just because we do need to control the etching. You want to make sure that you know what you've got in the etching and in the buffer layer growth before you start thinking about what's happening with the dots. So at the moment, so the next step is actually to move down to smaller holes and properly study the interaction. It is challenging, yes, yeah. It's taken us a long time to get that kind of quality of etching. Yeah.
There are perspectives to increase the separation of full microns?
Yes, sorry, I should. So we have. This is just summarising a lot of work that we've done. So I mentioned earlier that we use 4 microns here because we want to actually optically address individual dots. So our excitation spot is about 2 to 3 microns or so. So that means we want these separated by quite a lot so we can just look at individual dots. But when it comes to making, when it comes to investigating this, but also kind of making more advanced circuits, we would go to a smaller pitch. So actually, this is actually a 1.5 micron pitch here. We've gone down to even smaller pitches. But that all affects the site control, so it affects the occupancy because obviously it's related to the diffusion length. But interestingly, even with the large pitch of 4 microns, we get this high occupancy of the holes with the droplet. Less than 1 micron, yeah. We've gone down to, I think we've gone down to of the order of 500 nanometers, 300 nanometers, around 300 nanometers. Yeah. I mean, it's not, there isn't significant interaction between the holes in the E-beam process. You just need to be, as you get very dense, you just need to be slightly careful of proximity effects in the E-beam, but the etching process itself is fine.
Okay, John, I think we should move on.
Okay, thank you very much.